This is Unit 5.3. It deals with wave interaction. So on the left here we have two processes, reflection, so that's the wave bouncing off, or opposite to that is absorption. And sometimes one happens and the other happens with different frequencies, and that gives us the concept or the sensation of color. We also get speed change, so when waves interact with objects, particularly transparent objects such as lenses or glass, we get speed changes, and that leads to refraction if the angle is not 90 degrees. And we can use that, as we've said, to create lenses which will bend light in a very structured way, in a very useful way. And of course we have human-made lenses, but we also have evolution-created lenses, and we'll have a look a little bit about how that occurred. Our key idea here again is radiation transfers energy, so all the time light is being sensed, that is still a transfer of energy into your eye, into the eye. So here we're talking about electromagnetic waves and how they behave. So we saw a similar diagram for sound, and we mentioned then that the behavior was opposite, and we can see here now reflection is similar, but transmission isn't. It slows down. So light traveling through a vacuum or through air, it's slightly slower in air, but it's significantly slower in glass and diamond and so on. Still incredibly quick. I mean, half the speed of light is still very, very fast. And finally we have absorption, which is similar to sound, that although it speeds up, it doesn't get very far into the object. So here then we have a more detailed look at refraction. So here we've got a light front coming in, and as we said, it slows down as it hits the object. But this lower portion, if we look here, hits the glass first, so it slows down first. And the standard analogy is a line of soldiers. They'll wheel round, so this top part is still moving, and so the whole front changes, and we get this change of direction. Now the frequency of the light does actually make a bit of a difference to how much it slows down. So blue slows down a lot, red doesn't slow down as much. So they bend by different amounts, and that creates dispersion, and we can see that here more clearly. And this was an experiment done by Newton, which gave the first clues as to the real nature of light, the idea of frequencies, and it was a really crucial experiment. So here we have the formation of an image. Now this is really fascinating, I think, but it takes a little bit of time to understand, so we'll spend a little bit of time here. So here we have a source of light, and it goes off in all directions, all conceivable directions. We're only showing a few here. The one that concerns you as an observer is the cone of light that happens to hit your eyes. Everything else is, for you, irrelevant, but there's nothing special about your position. This is the key point. There's light hitting your forehead, it's hitting your shoes. You can see that because you can crouch or you can jump and you can still see the object. Now I've written effectively parallel here because it is very close to being parallel, but we mustn't forget that these four rays came from the same point, and it only makes sense in terms of forming an image that they come back to the same point, and that's what focus means. It means coming back to the same point, and that's what the lens does for us. So by being just the right shape, there's a refraction here, refraction there, so bending because of the speed changes we saw, and that, as I said, allows this light that started off in the same place to all end up on the same part of your retina. And of course this is happening many times over for the yellow and the green, and that creates the image. It's an upside down image just because of the geometry, but that's what's going on. So light goes off in all directions, it's completely chaotic, and the lens brings it all back into order and brings all the light that started from one point back into the same point, and therefore the retina and the brain can make sense of what it's seeing. So here we have the same idea, a little slightly different perspective. Here light is diverging, and our lens is able to bring it back together, and we call that a real image, so it can be projected onto a screen. Now here we've got an object that's too close really, and we have another lens here which is trying to bend it sufficiently, but you could never project it onto a screen here because, as you can see, they're not joining up. So here we've got still got divergence. So we've got divergence here, still got divergence. Here we've got divergence and afterwards convergence. So you need convergence for something to end up on a screen. Now the eye does actually do the converging for us, but we still would refer to what we see as a virtual image because your brain doesn't really understand lenses, and it would see it as though, and this is the key phrase, as though the light was coming from here, from this position here. And these dotted lines are not animated, as you can see, because there's no real light here and there's no real image there. So a mirror is an obvious example of this. We see a copy of ourselves, but we know it's not really there. Now here is the promised evolution of the eye, which I found is a really fascinating topic. So to begin with, we had patches of light-sensitive cells. Plants interact with light all the time, so it's not a big step for something to respond to the energy that's hitting it. Now, evolution is always about being slightly better than everyone else. You don't have to be brilliant straight away. So for a limpet, sensing light versus dark is useful, but there's no image here. Everything's just chaotically ending up on the retina. An improvement for the Nautilus is the pinhole camera. So there's a restriction here, which means that only certain rays can come through, and that creates a crude image, but a very faint one, because we're restricting a lot of the light. And this is why a lens is brilliant, because it's the best of both worlds. We get a very sharp image, but we're using all the energy, all the light. And it does it because it, as we've just seen, it regroups all the light that came from one point that ended up in all different parts of the lens, but directs it to one part of the retina. So we get a light from only one point in our view field, ending up in one position there, and that gives us a nice, sharp but strong image. So here we have short and long-sightedness and how we adjust for it. We can see on the left here a lens that's changing shape. We can see it's getting bigger and smaller, and that will end up with a different focal length. So if your eye is slightly too fat or slightly too thin, it'll end up in the wrong place, and we can put either a concave or a convex lens in front of that will adjust and make sure that the light again ends up on your retina where it should be, and not in front, or it never actually joins behind, but theoretically ends up behind. So ray diagrams, you've seen a few of them already, but it's a way of representing what's going on. So here's one way of representing what's going on, and here we have just a single line. So we have the angle of incidence and the angle of reflection. They are always equal. And here we have the angle of incidence and the angle of refraction now, which are not equal, depending on whether you're entering or leaving a block of glass. Up here we can see a little bit more detail, the effect of density. So we've got progressively denser material, slowing down the points of light more strongly, and we can actually create a number called the refractive index that tells us how this material behaves, but it's a measure of how strongly it bends the light, essentially. And you can see here 1c is the speed of light. Here it goes down to 0.9 c, so 90% of the speed of light, and we get not very much refraction. Here it's 70, and this number then goes up. The bending power goes up. Here we have two kinds of reflection. So in this scene, we've got light from the sky here hitting the bank, but the bank is pretty rough, so it will send off light in all directions. This is scattering. The pond here, by contrast, is very smooth, and it actually can preserve an image, and it reflects it perfectly. Specular reflection is a very neat reflection in essence. Finally, then we have color. So here remember we said that red, green, and blue are what we think of as white light. If those three hit our eyes in equal strength, we see white. So here we have a red object. Well, what makes it red is that it absorbs the green and the blue, as you can see that, but it reflects the red, and that's why we agree, or we describe it as red. Here we have the same idea, but the absorption here is different. There's no reflection. We have transmission. So this is a filter, or a piece of red glass, or a piece of red plastic, and it it transmits the red light, but it absorbs the other two. So it's just two ways of creating red.